An important concept in statistical mechanics is the equipartition principle. Let's look at what this principle tells us. Let's take a look at our energy level diagram again. Let's imagine that I have enough energy in my system that corresponds to the amount of energy required to excite an electronic state. So I've added a large amount of energy to my system. And let's add that energy as thermal energy. When I do this, that entire amount of energy does not simply go into exciting the electronic energy of the molecule. Rather, that amount of energy is partitioned, divided up between translations, rotations, and vibrations. And so I will excite the easily excited translations until I get to the next rotational level, and then I have enough energy in my molecule that my molecule starts to rotate faster. When I get enough rotational motion in my molecule that I'm getting close to the first vibrational excited state, I can get to the point where I can transfer some of that energy into making the molecule vibrate at a higher amplitude and thus excite the vibration. So I will use that energy to excite all of the different motions of the molecule rather than simply using the entire amount to excite one motion. Thus we say that any energy transferred into the system is partitioned equally between all modes of motion. The average energy in a particular mode can be calculated using the classical average value theorem by summing up the energy times the probability that that energy occurs divided by the normalization factor or the partition function for that particular mode. Translations and rotations are both kinetic energies and both depend on the square of the velocity, the linear velocity for translations and the angular velocity for rotations. Vibrational energies depend on the square of the distance between the two vibrating nuclei according to Hooke's law. Thus, the energy for any of the motions is dependent on the square of some parameter, whether that's velocity or position. If we replace the energy in our expression for the average energy with ax squared, since the energies are all proportional to something squared, we get the following expression. This expression can be solved to give us 1/2 k Boltzmann times T. And so the average energy in any given mode is 1/2 kBT. For a nonlinear molecule, there are 3 translations, and so there are on average 3/2 kBT of energy in translations. There are also 3 rotations, and so there are on average 3/2 kBT of energy in rotations as well. That leaves 3n minus 6 vibrational modes. What we need to remember is that vibrations have both kinetic energy and potential energy associated with them. Each of these types of energy contribute 1/2 kBt per mode. So each vibrational mode contributes in total 1 kBt per vibration. Since the amount of energy required to excite translations and rotations is not all that large, these modes contribute to the equipartitioning of energy nearly all temperatures. On the other hand, vibrations require much more energy to excite, and therefore not all vibrations can be excited at a given temperature. Only vibrations with small enough energy gaps can be excited and are thus considered when we're talking about equipartition of energy.